Does that work? Yeah? Okay. Hey guys. So so for those of you who were here yesterday, we're going to continue solving some of these problems. And so we've posted these online now, but not the solutions just yet. So we're going to finish going through this vector processing question that we started with. And then in the second half of lecture, Yuan is going to come and solve some other types of problems. Yeah. I think so. Will there be like a video recording, a podcast? I think we have to ask Yuan when he comes here, but to be sure. But yeah. Okay, so yeah, we have a couple more problems to go through then. So okay, I guess we'll just start with it. So just so you guys remember, this is the vector processing question that we started last time. And so we have a machine that has so it has 6 different possible instructions, including the load and the store. And we have some assumptions about how the memory works and whether we have chaining or not. And so we went through and we did parts A and B, which said that what are the minimum number of banks that are required in order for memory accesses to never stall. And we said that for 2 functional units, so we have 2 load and store functional units, and every memory bank has 2 ports. And so at any given point in time, one functional unit uses one of the ports. And so since memory has a 50 cycle latency, we need more than 50 banks. And so the nearest power of 2 there is 64. So we assume 64 banks so that both load store units can keep busy every single cycle. And so we did part B as well, which said that the machine executes the following program, and it has 111 cycles. So what is the vector length? And so we went ahead and did the timing diagram, and we, I don't know, can you see that? Yeah. So we drew the timing diagram out, and we said that the first load takes 50 cycles, and then the length of the vector minus 1. The second load starts starts 1 cycle later, and it does the same operation. And then we have the add, which takes 4 cycles, the mul, which takes 16, and the right shift, which takes 1. And all of this comes out to 111 cycles with a vector length of 40. So we know that the vector length here is 40. And so we said if the machine does not support chaining, but we can still do independent operations, we can still pipeline them, how many cycles would be required? And so what we found was that we can still do the loads one after another after 1 cycle, but we have to completely wait for these to finish before we start the other operations because these are dependent on the first ones. And so if the add takes 4 plus the vector length minus 1 afterwards, then 16, then 1, and we end up with 228 cycles. So this takes considerably longer. And so we're starting with part C, but we ran out of time, so we'll resume there. And so part C here says that the architect of the machine decides that we need to be cheaper with the memory system, and so we're going to cut the number of banks by a factor of 2. And so instead of having 64 banks, we have 32 banks. And so we're using the same machine as before, but with chaining, and we're trying to figure out how many cycles the program takes now. And so we're just going to start a new timing diagram. Is there like blank paper I should use? Yeah, okay. So the diagram we had before looked like this, right? So this is the initial diagram. And so we're ignoring this first fetch cycle because we're assuming it's already included in the latency, right? So, yeah, okay. So we have here the initial load is happening in 50 cycles, after which we get the rest of the 39 loads back 1 cycle, basically with 1 cycle latency each. But now we're unable to do that because for each functional unit, we only have 32 ports available. And so once we issue the first 32 loads, there'll be no more ports available for this instruction to continue. And so it'll have to stall until the first load comes back. And then it will, so then after the first load comes back, then we can issue the next set. So what happens is we have the vector load as before. And so the first load happens just like everything else. So we have 50 cycle latency. And then we have 32 banks, and we have 32 ports available for this, and so we can issue 31 more instructions. We can issue 31 more loads, and so the next 31 loads will come back. After the first one comes back, we can issue the next one because the ports are now free. So we incur another 50 cycle latency for the first one to come back, and then we get the rest of the loads back sequentially. And so since our vector length is 40, we get seven more loads back here, right? And so 1 plus 31 plus 1 plus 7 gives us our 40 total data elements. And so the second vector load happens, except this one's delayed by 1 cycle, right? And so it's exactly the same pattern. So we have 50, and then we have 31, and then we have another 50 latency to deal with, and then we get the rest of the 7 elements back. And then, since we're assuming a chained machine and all of that, the rest of the machine proceeds just like before. So we have a vector add, which takes 4 cycles of latency after the first load comes back. So some of the vector adds will start here once we have our load data, but the ones that limit the execution of the program are actually at the end here. So this is the very last series of loads. And so the vector adds that actually limit the execution of this program will start here. So we have the add latency of 4, and then we have 7 more elements to process, right? And so, so then we have the mul, which will begin executing 4 cycles later. So we have the mul takes 16 cycles, and then our 7 data elements, and then our write shift, which takes just 1 cycle, and then 7 data elements. And so this is our timing diagram now that we have bank contention because we have fewer banks. And so we can basically just add this up and see what we get. So here we have 1 plus 50 plus 50 plus 4 plus, oops, it's off, right? Plus 16 plus 1 plus 7. And so this is basically what this is like, 129. So we have 129 cycles for this program to execute with the reduced number of banks. Okay? And so here, so in the solution sheet, we just write 129 cycles. Okay? So the last part of this question asks that now we try and cut costs even further, but we reduce, but by reducing the number of banks even further to a lower power of 2. So it's a power 2 less than 32, right? So either 16, 8, 4, 2, 1. And the program executes in 279 cycles. So now we have to figure out how many banks are in the system, right? So we're kind of doing the opposite problem as before. So the best way to approach this again is with yet another timing diagram. So this is what we had when we had a bank size of 31, right? So now we're going to redraw this diagram for a bank size that is smaller. Yes? No, yeah. So you'll get partial credit depending on what mistakes you make. So if you show all your work, so the best thing to do is like to show your steps on the paper and then state any assumptions you might be making if like part of the problem is unclear or something. And based on all of that, we can take that into account when grading the problem. So yeah, it's not just like a number in a box, right? We're not just going to be like, oh, the number's wrong, everything's wrong. Yeah, okay. So, okay, yeah, any other questions before we continue? Okay. So for the second part, we're going to assume that we have a variable bank size. And so all of the stuff we did here with having to do an extra round of loads is going to happen again, except this time this number 31 and this number 7 is going to be a variable. So we draw a timing diagram again, except so the first load begins with a 50 cycle latency, and then we have the number of banks minus 1 loads. Right, so where B is now the variable which represents the number of banks. And so suppose that number is very small, that we'll do another round of loads. So we'll have another 50, and then we'll have another B minus 1 loads come back. And then so forth, we'll keep having more and more of these rounds until the very last one, which has a cycle latency of 50, and then we'll have some number of extra loads here. And so this number actually depends, so I'm going to call it x. It depends on whether the vector length is divisible by the number of banks, right? So if the vector length is perfectly divisible by the number of banks, then x would just be 0 and this round of loads wouldn't have occurred. But if x is not divisible by 0, then it could be anywhere from 1 to the bank size. Well, bank size minus 1. And so this is our representation for the first load. Our representation for the second load is the exact same thing, but shifted by 1 cycle, right? Because we're assuming that each load uses one of the ports from each bank. So our second load is just a 1, followed by all of this exact same stuff, right? So we have a 50, and then we have a B minus 1, and we have another 50, and then we have a b minus 1, and then so forth until we have our 50 and our x. Okay, and so now that we have this, we can just quickly add the other instructions. So the vector add is, again, it's very simple. Like this, the number of banks doesn't affect the arithmetic operations at all. So once we get the first load from our very last batch back, that'll be the one that, again, limits the execution time of this program. So starting here, we have 4 cycles for the add, and then we have x elements that come back. And so for the mul, we have 16 cycles, and then x elements that come back. And then the right shift here, which is 1, and then x elements that come back. So using this, we can actually put together an expression for how long this program takes to execute, right? So we have 1 plus we have 1 plus some expression that represents the time from here up until the first load, right? So this time here. So you can try and express this mathematically, but it would depend on 2 different cases that we talked about, whether x is divisible by whether the vector length is divisible by the bank size or not. And that would let us determine what x is. And then so we have that expression, plus 4 plus 16 plus 1 plus x, right? So we have some sort of expression here, and we know that this execution time is equal to what the question stated, which was 279 cycles. So we know this is equal to 279. And so there's a couple of ways you could go about this now. So you could try and express it more mathematically, in which case you'd have to think about like x as the remainder term when you take maybe the bank size, the vector length modulo the bank size. Or you could just take the approach where you just plug in numbers, because we know that the number of banks is going to be one of these guys, because it's just a lower power of 2, and we could plug these in and go ahead and figure out which number actually works. So I'm just going to go ahead and say that 8 ends up being the one that works, because I don't want to spend time going through math instead of the problems that we actually have. But so once you go through this, you find out that 8 is the right number that ends up giving you 279 cycles. And so by drawing the timing diagram, you can directly figure out exactly how many banks are necessary. Yeah, I don't know. I'd like to move on to the next question because we have a bunch that we can go over. But if you want me to spend more time on this, I can do that too. So is there anyone that really wants me to show this out? No? Okay, so I'll go on to the next question then. Which one should be next?
Because if you see the answer is 8, and the x would be 0, there would be 0 rest, and that doesn't give 279.
So x would be the last batch in that case. So x would be 7 here, because x represents the last batch size minus 1. So we'd have 7, 1, 16, 4, and then we'd have 50 replicated vector length 40 divided by 8 times. So we'd have 5 times 50, right? So 5 times 50 gives you 250, and then the extra 1 from here, because it's limited by the second load. So we end up with 1 plus 250 plus 4, 16, 1, 7. Yeah, so it's the last batch. So here we have a batch of 50 and then b minus 1, right? And so if bank size is 8, this is 7, right? So one set of loads takes 57 cycles. Then the next one starts here. We have 50 and another 7. And then we have 50 and another 7. And so the very last batch will be 50 and then 7, right? So we basically have 50 plus 7 times 5. Yeah? Okay. Yeah, does that make sense? Okay. Yeah, so these are online. You can go ahead and try this yourself, and I guess we'll be posting the solution soon enough, so you'll have those as well. Okay. Which one next? Should we do microcode or the cache? Yeah? Okay. So we have a question about tracing the cache. So we spent a little bit of time looking at caches, and so this goes over some of the more fundamental concepts of caching, right? So in this problem, we're saying that we have 3 types of CPUs. We have the 6808D, T, and F, okay? And all 3 of these CPUs feature one level of caching. So the system looks sort of like we have a CPU here, and then we have an interface to a cache, and then the cache interfaces with memory. And so each one of these CPUs has a different type of cache, right? And so we're given that the cache size is 128 bytes, and the cache block size is 32 bytes. So that tells us that precisely four blocks fit in one of the caches, right? And we also know that the cache uses the least recently used replacement policy. So the only difference between these three caches is the associativity. So we're given that D uses a direct mapped cache, T uses a two-way associative cache, and F uses a fully associative cache. So if we go ahead and draw these out, then we're saying that D is a direct mapped cache. So every single block, it gets its own set, right? So we have 4 different sets in the cache, and there's only one way. The design T uses a two-way set associative cache. So we know that there's 2 sets and 2 ways because there's precisely 4 blocks in this cache. And then cache F has a fully associative cache, so there's only one set which contains all 4 blocks. Right? So when each of these caches store a block, in D, it's mapped directly to only one set. With T, it's mapped to one of these sets, but it could go in either way. And with F, all blocks are going to be mapped to this one set, but they could occupy any of these ways. Right? So we have these 3 caches. So then we're told that we run this particular program to evaluate the CPUs. And this benchmark tests only memory read performance by just issuing a series of reads to the caches. And so we're going to assume that the caches are empty before we run the program. Okay? So the cache accesses that are generated by the program are as follows in order of access from left to right. So we have a sequence of accesses to a bunch of different blocks. So these are accesses to the cache by the program. So they're what's going on this bus. So every single letter here represents a unique cache block. And all 8 blocks are guaranteed to be contiguous in memory. However, the ordering of the letters does not necessarily correspond to the ordering of the blocks. So it's a mystery for us to solve. We don't know how these fit together. And then we're given that for the D cache, the direct mapped cache, we observe the following sequence of cache misses in order of generation. And so the cache misses are when the CPU requests from the cache, but the data does not exist in the cache, and so the cache has to go out to memory to get the data. So the misses are what's going on this bus. And so by using these above traces, we want to figure out which cache blocks map to the same set for the 6808D processor. And so we can say a couple of things right off the bat. So we have 8 cache blocks that are contiguous in memory, but we only have 4 locations in the direct mapped cache. And so by looking at some of the bits in the address, these cache blocks will be mapped into precisely one of these 4 sets, right? So given 8 fitting into 4, we're going to have 2 cache blocks mapping to each set. And so we're basically looking for pairs of cache blocks that belong to each set. So we have the sequence of accesses and we have the sequence of misses, so we can begin taking a look at how to go through this. So let's draw out an empty cache here. So this is what our cache is going to look like at the beginning of the program with nothing in it, and these represent the 4 different sets. So at the beginning of execution, we have this sequence of accesses, which starts with A, and we have this sequence of misses. And so when the program first requests A, it doesn't exist in the cache, and so we generate a miss, which makes sense because it wasn't in the cache previously. And we don't know where it belongs in which order, but we know that it's going to be in one of the sets, so we just assign it a location. So this A generated this miss. Then we have B, and B also generates a miss because it hasn't been seen in the cache yet. But we don't know where it goes because it could be in the same set as A or it could be in a different set. So we're going to leave it alone for now. Then the program requests A again. And A appears to generate a miss. And so this means that A was kicked out of the cache when B was brought in because B has been the only thing in between. And so that tells us that A and B have to belong to the same set because when B was brought in, A was kicked out, and then A comes back in and A generates another miss. So this sequence of misses comes from these guys. Then we bring in H, and H generates a miss because it's not in the cache yet, and so we can arbitrarily assign that a location. Note that you can't put H here, right, because we already said that there can only be 2 cache blocks per set because these blocks are contiguous in memory. So then we bring in B, and B appears to generate a miss, which makes sense because A was the last thing that was brought in. Then we bring in G, and G generates a miss, which again makes sense because it's not in the cache, but it's the same problem. We don't know where to put it, so we're going to leave it alone for now. Then we bring in H, sorry, we don't bring in A, but we try and access H. And H does not generate a miss. So that means H is already in the cache. And when we brought in G, it did not kick out H. So G has to belong to a different cache set. Otherwise, H would have been kicked out and it would have generated another miss. So G is responsible for this. H and H are both already in the cache, so they're just hits in the cache. Then we bring in A, and A generates a miss, which is true because B was brought in previously to kick it out. So then we have E, and so E generates a miss because we haven't seen it, but we don't know where it belongs. Then we call H. We try and access H, and H does not generate a miss. The next miss is actually D. So H is still in the cache. So we know that E must go either here or here, but we're not sure which yet. Then we access D, and D generates the miss. So yeah, D has not been seen in the cache, so we're not really sure where it goes either. H is the next access, and it generates a miss. So we know something kicked out H. But the thing that kicked out H could not have been E, because we've already shown that E cannot belong to the same set. So that means that this cache miss from D had to have kicked out H. Otherwise, H would not have needed bringing back in. So D has to be there. Then we try and access G, but G does not generate a miss. And so that automatically tells us that G is still in the cache, and so E has to belong here. Okay? And so G is a hit. Then we have C, and C does generate a miss. And so C has previously not been seen in the cache, so we also don't know where it goes. Then we have another access to C, which is a hit because it's already there. And then we bring in G, and we see that G is a miss. So G has been evicted in the past, and the only thing it could have been evicted by is C. So G has to belong with C. And finally, the only thing that we have left is F. So at this point, we know which cache blocks belong to the same set, right? And so this is our solution. So we can say A and B belong together, H and D belong together, G and then C, and then E and F. Right? So we've solved part A at this point. Are there questions about this part before we move on to the next one? Okay. So part B asks us to write down the sequence of cache misses for the F processor in order of generation. And so F is our fully associative processor, and our fully associative cache. And so we know that in the fully associative cache, every single one of these cache blocks will map to just the only set there is, but it can occupy any of these positions. And we're also told that the cache uses an LRU replacement policy, right? So we know which ones get evicted when an eviction occurs. So can I get another paper? Okay. So we're going to go ahead and trace out these cache misses in their order of generation, right? And so we're basically just going to enumerate how all this happens. So we're going to draw a sort of just a model of what's currently in the cache. And so we have one set which contains 4 different ways, and we know the sequence of accesses that occur because it's given to us. And so we're just going to go ahead and go through one by one and simulate what's happening in the cache as we go. So I'm just going to transcribe this sequence really quick. So we have, just copying this down. Yeah, so that's probably enough to get going. So this is the sequence of program accesses, and so we can just begin simulating this cache. So the first A gets brought into the cache, and so it's a miss. So I'm going to denote that by putting an X underneath it. B gets brought in. It's also a miss because it doesn't exist in the cache, but we put it in a different way because there's free space. So that's a miss. A is a hit in the cache because it already exists here, so that's fine. H is new, so we put it here and mark it as a miss. B is already in the cache, so that's fine. G is not in the cache, so we bring it in, and it's a miss. H is already in the cache, already in the cache, already in the cache. So this is a more interesting one. So we have E, which is not in the cache right now. So it's going to be a miss, but we have to figure out where in this cache, what gets evicted in the cache. And so this is where the replacement policy comes in. So least recently used means we're looking for the cache line that hasn't been accessed, right? The oldest cache line, essentially. And so we can basically look backwards to see what's the oldest one that's currently in the cache. And since everything is kept in the cache up until now, we look at A, so A is in the cache, H, G. These 3 are all in the cache, and they've been recently accessed. And the least recently accessed one ends up being B. because it's the farthest. And so B gets evicted, and instead we put in E. So E is now in the cache. Then we have an access to H, which is a hit, and then we have D, which is not in the cache. So again, we have to choose something to evict. And based on the LRU policy, it's going to be not H, not E, not A, but G. So G gets evicted, and we replace it with D. And so that's a miss. Then H is still in the cache. G is no longer in the cache because we just evicted it. So now we have to pick what to evict next. So the least recently used, again, not H, not D, not E, but A. So A gets evicted, and we replace it with G. And G is a miss. C. So yeah, basically you just repeat this process for the whole set, for the whole set of accesses that we have, and you write these down in order here. And that's basically the solution for part B. Should I actually go through it all? Like, does anyone want me to actually go through it, or shall I move on to the next part? No? Okay. Yeah, so it's just a process of like manually simulating what's happening. Okay. So the next part says that for the T cache, and remember that the T is the two-way associative cache, we observe the following 5 cache misses in order of generation: A, B, H, G, and E. But unfortunately, our evaluation setup breaks before we can observe all the cache misses that occur. So using just the given information, which cache blocks are in the same set for this processor? So now we have very little information to go off of, but we have to reconstruct what's in this cache. So we actually have some information from the previous part as well, too, because so we know that these pairings already map to the same cache sets for the direct mapped cache. So A, B, H, D, G, C, and E, F. And what this tells us is that since these 8 are guaranteed to be contiguous in memory, we know that for the two-way associative, the two-way associative cache, if A and B conflict here, that means they have a spacing of 4 addresses between them. And here, they'll also conflict in the same set because by being 4 away, they're also going to be mapped to the same set in the with 2 sets here. So A and B will belong to the same set. H and D will be the same set. G, C, and E, F. So the same pattern is here. So we can use that information in combination with these 5 cache misses that we're given to figure out which ones map to the same set. So I'm going to draw an empty two-way set associative cache here. And we can go through and do the same process and figure out what's going on. So over here, let's see. Should I write this down again? I don't know. Do you think it's necessary? So we have our sequence, which is A, B, A, H, B, G, G, H, A, G. Okay, so and so forth that maybe we'll need more later. But so we observed these cache misses. So we're basically going through this process of simulating this cache again. And so so A. So the first program request is A. And so A is going to be brought into one of these sets. And so we just assume the first one. So A happens. Then B. And ordinarily we wouldn't really know which set B should go to. But because of the information from part A of this problem, we know that B should go to the same set. So B will be mapped in here, since we're a two-way set associative. Then we have an access to A again, which is going to be a hit. Then we have H. So we don't actually know where H is going. And so we have to look at the misses that we get. So H is a miss because it hasn't been seen before. Then we have B. And so B does not generate a miss. And so that means B was not evicted. But B was also not the LRU here. A was the LRU. No. Okay, sorry. Yeah. B is the LRU. And so B would have been evicted by H if it mapped to the same set. But it wasn't because B did not generate an additional miss there. That tells us that H maps over here. And by default, we also get that D maps over here. So that misses H. Then B is a hit because it's still in the cache. G comes in and G generates a miss. So G, we're not sure where it goes. H and H are still hits, so that's fine. So G could still be here, and it also could have evicted the LRU, which in this case the LRU is B. So then we have an access to A. And so A does not generate a miss, which is fine because the LRU is B and A is still in the cache. Yeah, yeah. So then we bring in E, and E generates a miss. So E also gets mapped to one of these that we're not really sure which one. But we note that G and E come from different pairings. Then we have H, which H is already in the cache. This is... Wait, yeah, I think I missed something here. So... Yeah, B...
That means G wasn't on the first side, it was on the second one.
That means G.
G is right next to H.
Yeah, G is required to be here because A did not generate an additional miss before E, yes. So G is guaranteed to be here. And so that means C is also here. And H is paired with D, so D also maps to this set. And then the only pairing left is E and F, which have to go here. So that basically gives us our different sets here. So we know the cache blocks that map to these sets are then A, E, B, F, and then H, D, G, C. Okay. Yeah, so let's go through this again. This one's a little interesting. So I'm going to do the same thing we did before, where I'm going to write this down here, and we're going to trace the misses. So we have A, B, H, G, E, which are our sequence of misses. Okay, so we start off with an empty cache. So we bring in A is a miss. We bring in B is a miss. And we know those go here. Then A is a hit because it's here. And A is now the LRU, right? So we've got to keep track of that. Then H comes in, and H generates a miss. So H gets brought in, but we're not exactly sure what H gets brought into. However, B is the LRU at this point, and so the next access to B does not generate a miss, right? That means B is still in the cache. And B would have been evicted if H was mapped to this set, right? Because B is the LRU. So that guarantees that H has to be down here, right? And so we know that from these pairings up here, this gives us more information that we know D is in this one too, right? So after that, B is a hit because B is still here, and now A is the LRU, right? So I'm just going to write that down. A is the LRU right now. And then we have G. G generates a miss. We're not exactly sure where G comes in. So G could be in either still. So G. Then we have an access to H. And H does not generate an additional miss, right? So H is still in the cache. So H and H are hits. So these two are hits. Then we have A. And A does not generate a miss, right? Because the next miss is E. So we know that A is still in the cache, which means that anything new that had been brought into the other set. So what we've seen now is that G. So we know that G has to be here, because otherwise it would have evicted A. And then the next miss we see is E. So this gives us A, B, H, and G, which is basically enough information to put everything together at this point. So A and B are here. H goes with D. So H and D are here. G goes with C. So H, G, D, C are all in the bottom one. And then the only ones left are E and F, which have to be up here because, again, like these 8 blocks are contiguous, right? So that's how we get these results: A, E, B, F, H, D, G, C. Yeah. All right. Was that clear to everybody? It's a little more confusing than the first part, so like takes more thought. But yeah. Why D belongs to H and G? Because so if we look at like what the addresses actually are, right? Let's say that 3, 4, 5, 6. So we know that A, B, C, D, E, F, G, all those letters fit into this 8 contiguous memory segments, right? So the 8 contiguous memory locations. So like we can just think about this being like, I'll give an example, I guess. So we could just think about, sorry? Oh, yeah. Okay, but it's all about like, A and B would have to be off by 4, right? In order to map to the same set over here. Because you're using specific bits of the address, right? So it's like modulo 4. And here, this is modulo 2, which anything that's modulo 4, it's going to fit into here. And they're going to map to the same set here as well. So yeah, it's pretty important that the 8 are contiguous, because if they weren't, then you have no way of really knowing anything. Okay, so the next part of this question asks you to write down the sequence of cache misses for the T processor in order of generation. So we essentially follow the exact same prescription that we did here, where we go ahead and simulate the cache, except this time we're simulating the T cache, given that we know which one's mapped to which set. So should I do this or should I skip it? Because it's literally the exact same thing. You just go one by one and track whether it's a hit or miss, and then you just simulate the state of the cache. Yeah. Okay. So I'm gonna skip that. So does anybody actually want me to go through it? Like, just raise your hand or something, because yeah. Okay. So I'll skip that one. So then, the last part of this question asks you, what is the cache miss rate for each processor? So they're asking us for D, T, and F. And so we've already done all this work, actually. So if we go ahead and look at this sequence right here, we know exactly how many hits and how many misses we get. And they give it to us for the direct mapped cache, so we don't have to do that. We now know it for the fully associative cache, and we would have just done it for the two-way cache. And so we have all that information. So we literally just count up how many misses we have divided by how many total program accesses there are. And it just gives you a number, right? And so that would be the cache miss rate. Okay. Yeah, so that's the end of this question then. So, yeah, do you guys have any questions, or should I move on to the next one? No? Okay. Second? It's not going to be short to explain. The systolic. Okay. Okay, yeah, I'll start with a question about microprogramming. I guess we'll have the break, and then Daryuan will take over and give some other types of problems. Is he here? I don't know. Okay, so we'll start with this and see where we get. So this problem gives you. Okay, yeah. So this text is very, very tiny, but it's it's just some information. So this particular question gives you a data path, and it's a sample data path with a bunch of signals all throughout it. So actually, I'm going to zoom in a little bit. So that's the data path we get. So if you remember microcoding, it's where you design a processor such that you load specific signals from a giant ROM, and those signals will just control parts of the data path. So instead of having custom logic all over the place, you just have this very easy set of signals to just enable and disable parts of the data path to make an instruction work. And so here's an example of this. And so this gives us a single bus microcode-controlled implementation of the MIPS processor. So we have our giant bus around here that basically connects all the different elements. And every single part of the data path is controlled by a set of signals. So we have, like, for example, load enable for the instruction register. And then we have a register file read enable and a write enable and so forth. And so this, so going through the problem, so in a single bus processor, the interconnect between all these elements is the shared bus. And in any given cycle, only one particular unit can drive the bus. So you can only have one bus master at any point in time. And any other units may listen to it and latch the data that's on the bus. And so we're assuming that there is a microcode control ROM that can drive all of the control signals and specify the transition to the next state. And here they give us an example. So an example here is for a 3-register add instruction. So you're adding from one register plus another register into a third register. And so this is just the add states. And we're assuming that fetch and decode and everything is done by another part of the machine. So we're given just the microcode for the particular add instruction. And so going through these states real quick, we see that, for example, the first state latches RS into IDX. Actually, I guess I should give an instruction. So the instruction looks basically like the register file at register D is given register file at register S plus register file at register T, right? So that's the instruction that this microcode implements. And so the first two parts of the microcode here, they latch RS into IDX and then read the register file into A. So what this means is that from the instruction register, we basically enable, so the signals that we've enabled, so enable IR, so this guy's enabled, and the instruction register is written to the bus. And so any other data element can read from this bus and read the instruction register. The other thing that's enabled is a load enable of IDX. So in this IDX register, we have this register loading in this cycle, and the select field, which is this mux, is set to 21, which represents the instruction register fields 21 through 16, which are the source register, in this case RS. So by picking those bits, that gets latched into the IDX register in this cycle. All the other control signals are basically 0 because nothing else is happening. In the second cycle, we read the register file into A. And so that would require you to enable the read enable here, which would take the address, read out the data onto the bus, and then this register A here would have to read off of the bus. So let's see what happens. So the signal that's 1 is the load enable A, because we're trying to load the register A. The ALU is doing nothing. And we have the register file read enabled, so there's a read. And we're enabling the register, the enable register file to latch the data on, to put the data onto the global bus. And so that way we read out the data and then put it into A. And so these two basically take the first source register and write the value into A. So, okay, so yeah, so then the next two sets of states do the exact same thing for the operand B. And so this first one did RS into A, so this one's doing RT into B. And then the last two states latch RD into IDX, meaning we latch the destination register into IDX, and then we perform a write. So the write stage is a little more complicated because it does the operation A and B and stores it into the register file. So here we have the ALU performing an add. So the ALU is performing an add of A and B, and the ALU enable is set. So the NALU signal is a 1, so that the ALU result is put onto the data path. And then here the register file will take that data in and write it into the register that's supplied by IDX. And so we enable writes. So the register file write enable is set here. And so this basically encodes the add operation into 6 different states. And we see that they're all supplied as like state, next state. And so going from add 0 to add 1 to add 2 to 3, and eventually after we're done, we go back to the fetch state. So, okay, so this is basically the machine that we're given. And so for this problem, we're trying to implement a new instruction, which is called addm in microcode. And so addm does this operation where one of the operands comes indirectly from memory. So the register result is not directly added, but the data at the memory location supplied by that register is what's added to the RT register, and it's all stored into the RD register. And so we need to write out a microcode sequence, just like this table here, and in order to implement this addm instruction. And I don't know, should we? Okay, I'll briefly describe this, and then we can break. So we need to write out the microcode to implement this instruction. And we can assume that when we're accessing memory, the microcode sequencer will stall until memory gives us the data. So we're not concerned about like multi-cycle memory delays or anything like that. And so this problem is actually a lot easier than it seems because the implementation that they provide us with does almost all of the work that we actually need to do. So this add instruction that we need to implement is almost exactly the same as the add that's already implemented, except for the memory part, right? And so instead of loading the data from the register file at RS, we just need to load the data in the memory specified by RS into the register A. And so all it turns out being is you add one extra state in between here, in between these two, which instead of loading the register file into A, instead of loading the result of the register file into A, you instead load the result into the memory address register. And then in the next state, you add a state to perform the actual memory access. And the result of the memory access needs to be written into register A. And then everything else proceeds the exact same way. So it would come down to adding this extra line of microcode where we supply all the data signals in order to perform this operation. And then we modify this previous state to not write into A, but rather the memory address register. So I guess we can continue after the break. So go ahead and take a break until, what, like 15 past? I think, yeah, 15 past would be good.
Okay, so hello, people. Hello again for the last session. My name is Durian. You might have seen me before in some of the lab sessions, and I think I took 2 lessons from you guys a while ago. So last session, I'm here to show you the other parts of the exam material that would be covered in the final exam somewhere near the end of August. So as Minash and Hassan might have shown you before, this semester our course is composed of these 2 parts, right? And I'm here to talk to you about the questions mainly from the Harris textbook, okay? So here is a mock exams, kind of. Basically, it's a document containing some of the past year exams that are relevant, or at least that are covered in this course this semester. So we're going to quickly go over it so you know what kind of questions you should expect, okay? So here in the first page, oh, by the way, this is available on the website. You can download it later. So here on the first page, there's some really basic things like conversion between binary numbers to different number formats of different vertices, different representations, and maybe doing a little bit of ordering and asking you what the difference is between sign magnitudes, representation binary numbers, and say 2's complement. So these are pretty conceptual, okay? So try to earn all of the points here. Typically, you guys have been doing pretty well on this part, but sometimes there are mistakes here and there. So the second part, naturally, corresponds to what you've learned in the lab sessions. So these are primarily Boolean logic. So we typically give you like a truth table. And typically, when we give you a truth table, we like to ask you, well, basic things like, hey, what do the outputs here mean and how are they composed? For example, what do the x values here mean? And later on, we might ask you to simplify the circuit or represent the outputs using Boolean equations based on the inputs, okay? So try not to make any mistakes here because these are, again, really basic. I'm actually going to do one example later on. So here, later on, in these type of questions, maybe we might ask you to draw the circuits and maybe even ask you to compute the propagation delays. I'm not sure if this is exactly covered in the lecture this semester, but we're going to make sure before we test you on this. All right, so this is the second one that I included. This is for your information, and we're going to cover this a bit later on. Another part that is interesting relates to Lab 4. I hope some of you still have kind of a memory about what we did in Lab 4. Okay, so what we did there is we introduced these clocks into our circuits. We did synchronous circuits where you have blinking lights indicating which direction you want this Thunderbird car to turn, right? And remember in that lab, we asked you to design a state machine for this. So we're going to represent your design. You're representing your design using a finite state machine. And the transition between different states of these machines, different states in this machine, corresponds to the different inputs that the users give, okay? And these at the time, those were triggered by the clock. Now, naturally, transition between different states do not have to occur because of clock signals. They can also occur because of various inputs to the system. So in these type of questions, you're supposed to either design a finite state machine based on the given specs, such as here, or we give you a finite state machine and we ask you to characterize it or to describe what it does, to maybe correct some mistakes that it possibly has. Okay, so overall, these are the sort of the common questions that I have seen over the years. Other parts of questions might contain testing your knowledge on Verilog programming. So I'm not sure if this is still going to be the exam in the exam this year because we seem to stress this less this semester. But these type of questions basically test your knowledge on the correct syntax and programming you use in Verilog. Okay, so what you want to do is know your syntax, know how to write Verilog code, know that you can only put sequential statements within these always statements. That is, outside of always statements, you should always use assign to prepend whatever assignments you have for the values on the wires. And other things are the input and output types, the lengths, and some basic debugging skills. Okay. And finally, we might have a cache question that asks you to differentiate what kind of cache you have depending on different architecture. Now, I know that these two different textbooks have different approaches to introducing cache design to you. So we're going to find a balance, and we're going to maybe present maybe a few just unified view of the cache information. Okay, so these are the kind of questions you can expect. Basic binary manipulation, truth table and binary logic circuits, minimization of the representations of these outputs of the circuits, state machines, and Verilog debugging. Okay? Yes? So I can't speak for it because we haven't started designing the questions this year. But in the past years, we don't really separate between these two parts. We sort of mix them all together in the questions. But we will typically prepend every question with a theme, and it's from the theme that you can determine whether or not this was the part from the labs. Okay, but I've been getting actually quite a few emails from you guys who are wanting to keep the boards for practice during the semester. That's fine. If you are interested to do this, that's fine. But typically, just looking at the code would be sufficient to prepare for the exams. Okay. Yeah, that's unfortunately that's undefined yet, and but you can expect an equal distribution between all the things we test. Right? Okay. Did you guys learn LC3? Yeah? No? No? Just MIPS, right? Okay. All right. So in the past, you might have seen that we also have questions related to MIPS programming, where students are supposed to write assembly codes for MIPS. I have not put that in here because we're not sure yet if that is what we're going to test on, but we're going to make announcements later on. Okay, so any more questions? All right, so let's say 1 to 2 questions together, and I just want to sort of give you a refresh on how you can go about solving these questions. So let's have a look at this one together. So this is a truth table. And in this question, typically, you will be asked to derive the Boolean equations for 2 4-input logic functions. Which 2? These 2, A and B. All right? So 2 4-input logic functions. The inputs are D3 through D0, and the outputs are A and B. So these are 2 functions, A and B. All right? So I can already give you like a quick overview. The value of A is 1 when there are at least 3 consecutive 1s or 3 consecutive 0s in the input. Okay, but that is not really important. Basically, what you're given is basically any truth table, and we would typically ask you to derive a representation for this for this output A. Okay, and we typically ask you to minimize it to make it more compact, okay? So what we can do here is already for function A. I'm going to draw it over here. You can use the K-map. And transform the truth table onto this K-map, okay? So we would have, let's say, D1, D0 over here, and D3, D2 over here on the vertical axis. So these represent 0, 0, 0, 1. I think this is 1, 1, and 1, 0. Notice that this is not 1, 0, and this is not 1, 1 because we want adjacent cells to only have a difference, having difference of 1 bit. Yes? Oh, you covered this already? You didn't? Okay. Are you sure about this? Okay. All right. Well, then, if it's not covered, then this will not be part of the exam. But I thought this was covered in the labs already. No? Okay. Okay, that's fine. Then I will update the questions accordingly, and we're going to remove the truth table questions. Thanks for the heads up. All right. So, but I'm guessing the state machines are covered, right? All right, so let's do one with the state machines, okay? So, like I mentioned before, that actually saves a lot of time, by the way. So, as I mentioned before, with state machines, we often would like you to design state machines based on a given specification. So why don't we all look together at this specification over here and try to design a state machine, okay? I'm going to give you a, maybe it's not that clear. All right. Is it clear enough for you guys? So let's just have a read at this together, and we're going to solve it together, okay? All right, so maybe some of you have already finished reading the specs. So what we're designing here is a power-saving control module for some mobile device. Okay, so there are typically two inputs. These two inputs represent, let's say, the state of whether or not the device is charging or discharging. There are 4 power levels for the device, 4 modes for the power, and when you see these type of statements like 4 power levels, something that should give you an immediate indicator that, hey, these are the states that I want to model. Okay, and these states, whether or not the system is at either of these states, depends on the 2 inputs, C and D. When both inputs are the same, the power level does not change, so it stays at its current level, or maybe your current state. And when only C is active, by active I mean 1. Then the power level increases until the last level, level 3, is reached. Okay? When only D is active, then the power level decreases until the lowest level is reached. And the transition between these different levels are performed, let's say, by default using the clock. Okay? There are 3 other types. There are 3 outputs from this state machine, and the first one is dim. The second one is low. The third one is animation. So these represents that you want to dim the device, you want to indicate that the device has low power, maybe at a lower level you want to indicate this. And animations, it's, let's say, well, you're fully charged, you can do a lot of power, you can do a lot of applications. Right? So dim is active power. Dim is active or set to 1 at power level number 1 or lower, and low is active when the power level is at 0, and only then. Okay? And animation is active at the power level 3. And the rest, well, that's just for a better storytelling. The reset state corresponds to power level 2. So whenever there's a reset button pressed, the state should go to level 2. All right, so now we can imagine that there are quite a few levels here. Let's have a look at them together. All right, so I'm going to put this up here a bit. All right, so I hope it's clear. So 4 levels, right? Let's do 3 and 4. All right, so pardon the drawings. So I have level 1. Oh, sorry, the level starts from 0 to 3. So you have level 0, level 1, level 2, and level 3. And there are going to be transitions between these states, right? So let's first talk about the outputs. So in this question, we want you to draw a more type finite state machine, which means that the output depends only on the state. So we can already plot out the output based on the state. So for level 0, the output is always consists of the value for dim, the value for low, and the value for animation. Let me bring this up a little bit more. All right, so low, dim, low, and animation, right? So can anybody tell me, it's a small class anyways, yeah?
It just says that the adding is only active at power level 3.
Yes.
Is that now level 0? Or is that state?
Well, that means that the value anim is 1 at power level 3, which means that it should be 0 anywhere else, right? So for example, in this level 0 over here, the value for animation should be 0. That's what this statement means. Okay? And why don't I just fill in the rest for you guys, for at least first level 0. For dim, is active at power level 1 or lower. So since 0 is lower than 1, you would put this at 1. Okay? And low is active at power levels 0 only, and therefore low is also 1. All right? So we can also continue to fill in the values for these 3 outputs for all of the other states. Can anybody give me the answers for level 1? Yes, please. 1, 0, 0, exactly. So low is only 1 at power level 0, right? So 1, 0, 0. Animation is only 1 at level 3 later on. Okay, so for level 2, 0, 0, 0. There we go. Good. And level 3? Yep. 0, 0, 1. Good. 0, 0, 1. So these 3 outputs typically should be drawn inside the circles, but we're not really that strict. You just have to clearly indicate that the output values for these 3 variables are the corresponding values. And as long as they're correct, you get the points. So now the important thing is the transition, right? So how does L0 transition to L1? And how does L1 transition to L2? And L2 to L3? Anybody has any ideas? Yes, please. Excuse me? C and not E, yes. C and not D. Right, so essentially what this means is that C is 1 and D is, well, is not 1, it's 0. So you can either write it this way, or you can write C equals 1 and D equals 0. Right? Either way works. And what about L1 to L2? I'm guessing it's the same, right? Because it's still charging. So it's the same, and the same for level 2 to level 3. What about the other way around? What about from L3 to L2, L2 to L1, and level 1 to level 0? Any ideas? Yes, please. Yeah, the other way around. Not C and D, not C and D, and not C and D. Oops. Not. Okay. Right, so that's essentially it. What about the reset? How should the reset be put? So here in the statement it says the reset state corresponds to the power level 2. And this means that when reset is pressed, you want to restore the state into level 2, right? So remember, for every finite state machine, you should always have this initial state. We haven't drawn this yet. So given that reset resets to level 2, that would be your initial state. So you should always add this reset. And this is your initial state. Okay, guys? All right, so this is just one simple way of realizing a finite state machine based on the provided specifications. Like I mentioned before, there could be other ways of doing this, and also maybe other ways of testing you on this. Yes?
Don't we also have to do the loop, or are these just assumed?
Excuse me?
From level 1 to level 1, like staying, so it's neither charging nor...
Oh, right, yeah, so that typically, implicitly that is implied. So, but yes, it would be nice if you also write this to say these are all the other cases. For example, this is when C and D are the same case. And yeah, actually it represents this line, right? And also represents C, not C, and not D, right? So then you have all of the cases. And you do that for every state, right? Okay. Yes, please.
Do we have to do this, or is it optional?
It's nice if you mention it. So here it depends on the grading policy. Our grading policy is the following. For all of the explicit changes, all of the explicit state transitions, you should clearly mention them. And whichever that you don't mention, we're going to assume that's the That's the self-loop transition. Okay, so be sure that for all of the transitions that you draw, label them exactly correct. Okay, we're not that strict about syntax here. We just want to make sure that you provide the right answer. So if you miss like these self-loops, or you have these self-loops naturally, but if you do not write the labels, for us, that's okay. All right. So the solutions for all these questions, after I take out the truth table questions, would be put online later on. All right. Good. So, like I said, this is a more type finite state machine, and we could also test you on a Mealy type finite state machine. And in one of the questions later on, let me just show you right here. In this question, we show you actually a Mealy type finite state machine. Essentially, the output depends not just on the state itself, but also on the input. Okay, so and it's actually in this question we ask you to convert this state machine into the other type, namely the more type. So you should also learn or think about how you can do that. Okay. All right. So if that is covered, then we can maybe do one of the Verilog questions. So typically, these Verilog questions, we don't want you to waste time writing Verilog code, or at least writing lengthy Verilog code. Typically, we just have you write a small snippet. And for this question, we ask you to look at the Verilog code and see if the code is correct. Okay? So obviously, I'm not going to tell you the first one because you already see the answers over here. But let's take a look at the second one. So can anybody tell me if the second one is correct or not correct? Shouldn't be that hard, by the way. Okay, so it's correct. There might be some issues. People might be a bit confused as to, remember that for all of the statements you put in these sequential statements, for all of the values that are stated here as the output, they're going to be synthesized registers, so you should always specify them accordingly in the output, okay? And for the input types, it doesn't really matter. And you can always assign their values to other variables later on. So this is an example that is of a correct Verilog code. It's not really well written because obviously for B0 through B3, you can just assign it to Z. All right. Oh yeah, so that's fine because Verilog supports anyways either type of ordering, so that's fine. Yeah. So the question was whether or not the issue matters here with this 3 to 0 and 0 to 3. So these are just different customs. You can actually code it either way. So you can code it as a decreasing order for any typical binary number, or you can encode it like an array of bits. Yeah, it will change representation. Yeah. In this case, the 0th bit would be the most significant bit, which is actually not that intuitive, but it's still allowed. Okay, so these are some of the questions that I wanted to talk to you about. Unfortunately, I originally want to talk to you about these K-maps, but if they're going to be out of the question, if they were not taught during the semester, then they will not appear in the exams, obviously. But still try to be aware of basic Boolean operations because you might encounter them in some Verilog-related code. Okay? All right, so my brief part here is pretty much done. Are there any logistic questions for the exam here? So the exam format should be clear to all of you, right? So it's going to be 90 minutes. You have 6 pages of, you can prepare 6 pages single-sided of notes. and they can contain anything you want from either textbook or either textbooks or either material, any slides from the course. All right. Yeah, if my part is done, then I'm going to head off to these guys. And are you guys done as well?
I mean, I guess it's up to you guys. Like, do you want us to do more practice questions or like, or no? What do you want?
Can you still do number 8? The systolic area?
Yeah, we can do that.
Okay. All right.
Is it pretty much?
Yeah, please. Oh, definitely not. So for the parts that were not covered in the lectures, they're interesting for you to read, but they will not be in the part of the exam. This will be sure about, and we will do some internal reviews to make sure that the exams strictly abide by this rule. Okay. Yes.
So some of the supplementary reading material, is it, how critical is it to read it? So basically, if we just understand what is written in the textbook, is that not enough, or should we be fine?
What do you guys think? So we want to design the questions mainly on the course lecture slides, right? So supplementary material are typically just for your reading, because actually there are quite a few of you that are really interested in this. But we currently don't plan to have those as the major part in the exam. So if there's a change on this decision, I will definitely send emails around. But please expect that to be the current answer. Yeah. Just try to make sure that the lecture slides, you prepare for them. Yes?
But the kind of questions that we discussed yesterday and in the first lesson today could also be on our exam, right? So it's not just these questions that you just...
Oh yeah, of course, yes. Well, the thing is, this course currently contains materials from previous years about basic logic circuits and also about computer architecture that was added this semester. So both parts would be in parts of the exam. But the good thing is, exams from previous years, we only add them if they are also taught this semester. So you don't have to prepare for all of the exams that you see maybe in past year's exams from the FIS database. Okay? Oh, right. Go ahead. Oh, yeah, it's a good idea. We'll compile this and let you know, okay? And it's going to be corresponding chapters for the book and also the slides, okay? Sure, we'll put that on the list. Thanks. Okay, I guess you guys are up.
Yeah, can you hear me now? Yeah? Okay, all right. Yeah, so there's one more question that I guess we'll go over. It's the last one in the practice set. It's called Programming a Systolic Array. So, okay. Yeah. Where's the pen? Okay, so, let's see. Okay, so this problem deals with a couple of figures here. So figure 1 shows a systolic processing element, right? And so figure 1 is this guy here. And so this is one processing element. And we're told that each processing element takes in 2 inputs, which are N and M, and then it has 2 outputs, which are P and Q. And then every processing element also contains an accumulator called R, which is just like a data storage element. And this can be read from and written to. And the initial value of the accumulator is 0, right? So figure 2 expands upon this and shows an array of these guys composed of 9 elements. And figure 2 is this one. So we have 9 of these processing elements here, and then these are going to be input data tokens. So we have that array of 9 processing elements. And so we want to program this systolic array design to perform the following matrix multiplication. So we want the output C to be the matrix A times the matrix B, right? And so the matrix multiplication is, just like row times the dot product of like row times column, and then row times column to produce all the output elements. And so we have a bunch of like design specifications here. And so in every single time cycle, every processing element, which is this guy down here, will take in the 2 inputs, perform a particular computation, and then write the outputs. And the time cycle labels on the input boxes determine which time cycle the inputs will be fed into the processing elements. And so that means that over here, 0, 1, 2, 3, 4 mean like these data elements will be sent in here on cycle 0, and these on cycle 1, and these on cycle 2, and so forth. And same with these inputs coming this way, right? So every processing element takes in those inputs. And so any processing input element that is not driven will default to 0. And any processing element that has no output arrow will also have its output ignored. So the output from these guys is just basically discarded. And any input that we don't actually specify is just going to be 0. Okay. So after all the calculations are finished, each processing element's accumulator will hold 1 element of the final resultant matrix arranged in the correct order, right? So we want this output matrix, which is the 9 elements of C, to basically be encoded in these guys. And we can assume that the correct order is basically the same order as the input, and as the same order as stated here. And if we assume something else, then we should just say so. So we're going to go ahead and assume the same order for this case. So we want C00 to be here, C01, C02, and so forth. Okay, so we want that output at the end. So the question asks us, please describe the operations that every individual processing element performs using mathematical equations and the variables mn, p, q, r, which are the input outputs and the register here. So they give us empty fields for what should P be, what should Q be, and what should R be as a function of the inputs and R. All right? And so the second part asks us, please fill in all 30 input boxes so that the systolic array computes the correct matrix multiplication result described in the previous page. And the hint says to, you write it in terms of A, ij, and B, ij. Okay, so I'm going to leave the matrix up here. And then we have our diagram here. So it's okay, it almost fits. But so basically we want to arrange all these inputs of A and B into these input boxes such that this computation is performed correctly, right? So suppose that because we want the outputs to be like this, we will take a look at the first output, C00. So we know C00 should be composed of the dot product of this first row times this first column, right? And so we want A00 times B00 plus A01 times B01 plus A02 times B20, right? So we somehow need to feed those inputs into this box. So these A and B are going to have to go either here or here and be fed into here 1 per cycle, right? And so for the next processing element, for example, C01 is over here. And so we're going to want this series of A's, but then the next column. And so all the same A inputs need to go to this box, and also by the same logic, this box. So it would make sense to feed the A inputs this way, right? Because those are going to be used by all 3 of these processing elements. Likewise, for the B processing elements, we're going to use them for C00, C10, and C20, right? Because for C00, C10, and C20 will be the dot products of these rows times this particular column. So it would make sense to put them down here. So now it's a question of how we want to arrange the logic such that the output operation will be correct. So if we're passing the inputs from basically the same inputs are being passed to each of these 3 processing elements, right? In any direction we really think about. And so the same input element that comes in here, which is M, is also going to be the output element, P. So these two are identical. You don't perform a transformation on the input for this particular output. And the same goes for N and Q. So if we're just passing the elements through, then when we come to our equations here, we're just saying P equals M, because it's just a pass-through, and then Q equals N. And that's all that's going to happen. And then in order to perform the dot product, every cycle that we have two of these elements come in, we're going to have to perform element times element, and then accumulate the result, right? Because so every cycle we're going to get a new set of inputs. We're going to multiply them and add them to the accumulator. So what we really want is R equals the original R plus the inputs, the product of the inputs, M times N. So these are the operations that the processing elements will perform individually, right? And so the last part of this question is to kind of figure out how to organize the data such that we get this computation performed correctly. So we can think about this in terms of at what cycle the inputs will reach particular elements. So for this first element, in the initial, the very first cycle, we'll have data to compute with. So we want to put the first elements we can here. And so we can put elements here and here, and the cycle after, and the cycle after. And since there's only 3 we want to do, we can just leave nothing in the outer 2 cycles, right? So we can just have 0 inputs here, because we don't need to do anything. For this guy, it'll receive an input on the very first cycle here, but it will take 2 cycles to receive an input here, right? So we don't want to put a data element here, because otherwise we'll just have 1 input and then nothing here. So instead, we're going to pass the input from the second cycle. That way, when this one reaches this processing element, this one will also reach this processing element, and we'll perform the correct product. So we're going to have 0. And then by the same token here, it's going to take 2 cycles, so like 1, 2, 3 to get here. And so we want this data to also take 3 to get here. So we're going to have data here, meaning that these two will be zeros. And so by the same logic over here, it's going to take 2 cycles to get here. So we want this data element to come in at the same time as this one. So we're going to put 0 here and also here. So now we know we want to arrange our data basically in this fashion and then this fashion over here. And so we just have to add these inputs, right? So on the very first cycle, we can have this guy compute A00 and then B00. And then on the second one, we can have it do A01. And then over here, we can have it do B10 and then so forth. Sorry, is it off the edge? Oh, yeah, okay. So at this point, we're basically done with the problem. We're just filling in this table in terms of like at what cycle the inputs get here, right? So A00, A01, A02, and then here B20. And then for this guy, he's going to be computing the product of the first row, which comes in, I guess I got A and B backwards. Yes. Very good. Yeah. So I'm just going to write this again. So this is A00, this is A01, this is A02, and this is B00, B10, B20. Okay, yeah, so this guy's going to take in the 3 A's afterwards, and we're going to require the second column of B's here. So this is going to be B01, B11, and B21, and then so on and so forth. We just fill in the table, yeah? Okay. So yeah, that's both parts of this question, and if you just fill in the rest of this. So any questions about this one? I think it's a lot more straightforward than some of the other ones. So yeah, okay, yeah. I guess we have a solution sheet. So there you go. It's done. So yeah, okay, yeah. So any questions about that or any of the other questions in this solution set? Because otherwise, that's all we have, I guess. And so we'll post the solutions for these on the website after we clean them up and put them together. And there'll be a second set of practice questions. What are they called? The practice? Yeah, practice exercise. There'll be a second set of practice exercises that we'll also post, which will just be more problems for you to do and more solutions to look at. So yeah, hopefully all these are good preparation material that you guys can work with for the exam. Yeah, otherwise, thanks guys. I guess it's been pretty great. This is the last class, so I guess probably won't be seeing you guys in lab anymore. But yeah, it's cool. So yeah, thank you all. It's good.